Precalc students, we're going to do a linear programming example. So this example actually matches up with one of the problems that's in your assignment. You can figure out which one and then just add in the work right there on your assignment. So when we do linear programming, we're looking for trying to minimize or maximize some kind of objective function based on constraints that are given to us in the context of the problem. So reading through this example, we've got Pearson's Metals, and they mine two different ores, ore R and ore S. The company extracts minerals A and B from each type of ore. It costs $50 per ton to extract 80 pounds of A and 160 pounds of B from ore R. It costs $60 per ton to extract 140 pounds of A and 50 pounds of B from ore S. Pearson's must produce at least 4,000 pounds of A and 3,200 pounds of B. How much of each ore should be processed to minimize cost, and what is that minimum cost? The key thing in any kind of linear programming problem is to make sure you know what the variables are and how they match up. And the biggest deal is with the objective function. Always start there. So how much of each ore should be processed to minimize cost? So we're minimizing cost. This is how much of each ore. So ore would be these two variables right here. So we've got two ores, ore R and ore S. So R and S are going to be the variables that are within my objective function. Now I'm going to call it the cost function. So I'm trying to minimize the cost function. Well, what does it cost? Well, looking at some dollar amounts, it's $50 per ton. Now to extract 80 pounds of A and 160 pounds of B, that's kind of information that's not important in the moment. It's from ore R. So $50 per ton of ore R. So I'm going to put, as far as cost is concerned, it cost me $50 for a ton of R. Plus $60 per ton for a ton of S. Okay, and again, ignore the stuff in the middle for right now. So 50R plus 60S is the objective function. That's what we're going to try to minimize. Now, when it comes to the constraints, that's a little bit different story. That's where these other numbers are going to come into play. So constraint-wise, I look for things like at most, at least, and I notice in this sentence that Pearson's must produce at least 4,000 pounds of A and 3,200 pounds of B. Okay, so at least 4,000 pounds means that something has to be greater than or equal to 4,000 pounds. Okay. So this is going to be my A equation. I'm not actually going to use A in the equation itself. I just know that this is the amount of pounds of A mineral that we need. Okay, and then 3,200 pounds of B. So at least that. So at least 3,200 pounds of mineral B. Okay, and again, I'm not using those variables. I'm just telling you this is the B equation. Okay, so the variables that I'm supposed to work with I already picked out. It's R and S. So how do I use R and S in the A equation? Well, that's where these numbers become important. So 80 pounds of A in a ton of ore R. Okay? So for each ton of R, I get 80 pounds of A. So I get 80 pounds of A for each ton of R. I'm not sure how many tons of R I'm going to have, but I'm going to multiply 80 times R. That's going to be how many pounds of A I've got from the first kind of ore. Then I get 140 pounds of A from ore S. So 140 S would complete the A equation. Okay. For the B equation, well, I get 160 pounds of B from R and 50 pounds of B from S. So in the B equation, I'm going to go with 160 R plus 50 S. Okay, and that's got to be greater than or equal to 3,200, which I'll just put some blue over the top of this, just so that the color matches up. Okay. Now, another constraint that you could pretty much always assume with a word problem would be that X, no, I won't use X, R is greater than or equal to 0, because I'm not going to make or mine negative pounds of either of these kinds of ore. So that's just sort of understood. I'm only going to work in the first quadrant. So what I would do next, now that I've got my constraints, I've got my objective function, I'm going to go ahead and graph my system of inequalities that makes up the constraints, and I'll do that to find the feasible region. Desmos is an easy way to do that because I can just kind of type them in as is. So 80x, for R, plus, I believe it was 140y is greater than or equal to 4,000. So that was the number that I'm working with first. Greater than or equal to 4,000. And then the other one was 160x instead of r plus 50y instead of s. And that's also greater than or equal to, that one's greater than or equal to 3,200. Okay. I don't need the greater than or equal to 0 parts because obviously I'm only working with positive numbers. So here's the deal. If I zoom this out, the overlapping parts would be all of this stuff. Okay. So this feasible region is actually unbounded. Like you could have a maximum, like you couldn't even say that there's a maximum because it goes on forever and ever. But you could have a minimum value. And again, we're trying to minimize the cost. So the minimum cost is going to happen at the vertices of the feasible region. So I got a vertex right here at this point, a vertex right here at this point. Okay, so this, and then right here where the two equations cross is my third vertex. These 3 points will be the potential spots where a minimum may occur. So I'm going to write those down within Desmos. And again, I'll just draw a quick sketch. You could probably do the same. Here we got these. We got a green function that looks like, let's see, that was what, the red one? So green's like this, and blue is like this. And I'd label the points on each that I'm going to use. So I'm going to use this point here, this point here, this point here, because this is my feasible region out this way. So of these points, I've got, we had 50, 0, and 0, 64. 50, comma, 0, and 0, 64. Those are the two x and y intercepts that were pretty easy to find. You could have done that by hand if you wanted to. So 0, comma, 64. And this point right here, where they intersect, I'll just go with a rounded decimal there. So we'll go with 13.478 and 20.87. So 13.478 and 20.87, I believe it was. Yeah. And then what I'll do is I'm going to try all 3 of these points in the objective function to see which of them gives the minimum cost. Okay, so I'd set up maybe a little table just to organize my work. I'm going to call that intersection A and this one B and this one C, just for the sake of not having to write those numbers again. So I'm going to take A, plug it in that point. I'm going to take B, plug it in that point, and I'm plugging it into my objective function, this 50R plus 60S number. Okay. And then what I'm going to look for is I'm going to look for the different outputs that I would get, and I'll label one of those as being the minimum. So I'm not going to do the whole thing for you, but I pretty much have. You can finish it off and come up with those final numbers.